So first of all, thank you very much, Jean-Christophe and Corinne, for this very kind invitation to this talk, and thank you all for being here today. So I reduced the title. Why did I reduce the title? Because what I like to do, you may have seen in the abstract, this is a very biological talk, and I like to present the biological question first, before going to the method. So let's maybe look into this enzyme. I know most of you are not bio people, so I do my best to explain you why this is important to us to study this system. So, first question, why membrane proteins? You know, there are different types of proteins. Some they're called soluble, some are called membrane proteins. Membrane proteins are really interesting systems because, as you may know, they play a crucial role in everything that is linked to bioenergetics of the biological cell. So they're working horses for photosynthesis, respiration, cell recognition, signaling. They're really essential. So why they're so little studied? Of course, because it's more difficult. They have this surface that is covered partially by lipids, so they're amphiphilic and often relatively unstable. Still, it is manageable to work with them, and we think it's really exciting to do because they are, it depends which study you're reading, up to 80% of future targets of pharmaceutical industry. So getting a hand of them and being able to study them is something really important. Well, these reactions are all catalyzed by them, many others. I don't want to go more into detail. We will focus on this one, oxygen reaction, which is certainly a very important process, as you know. Respiration, we are very lucky. You know, when I started, when I was a junior, we had no idea how this was looking. I mean, there have been 80, 90 years of study on respiration, and then little by little structures came in many spectroscopy and biochemical studies, helping us to know how these absolutely efficient systems have been assembled. So we know a lot about the architecture of these big enzymes, and the respiration itself that starts with, well, let's be simple, complex 1, it goes over to complex 2, 3, 4. It ends at the terminal enzyme. I don't want to go too far into biology, but I think this reaction for you is obviously, it's the oxygen reaction coupled to proton translocation. You should know that the important part of the respiration is the proton pumping. So this is something that the system needs to do to create a gradient and to have the ATP reaction. Now, how is the oxygen reacting? When I started in the field, there was this kind of dogma. Everything works like in mitochondria. Of course, we know in the meantime this is totally wrong. But there was this idea, the oxidase, like you find it in mammal systems, is exactly the same, maybe a little adapted, but it will work like the mammal system. This is absolutely not true, which is interesting, because we want also to understand bacteria, and we want, when we understand bacteria, be able, for example, to develop new antibiotics. So, complex 4, keep in mind this is the oxidase. So we have, you see how many there are. A, this is us, this is mitochondria. B, C, what's the difference? The different subunits, different cofactors, even the nitrate reductase is part of it. Now the one we will be interested in, I'll explain you why, the BD, and then there is one without cofactor. Now, why is the BD so exciting to us? It's a system that it's known in 20, 30 years, and it was kind of the little cousin of the oxidase that is activated when there is less oxygen, stress condition, nothing very special. However, it is only present in bacteria. Now, let's come back to the question, we want to develop antibiotics. So there is a target. This is a potential target. So let's have a look at that. First structure came out in 2016. Why so late? Because it's a full membrane protein. It's really like a little ball in the membrane. It's really highly protected by the bacteria because it is a defense factor. This enzyme can catalyze the oxygen reaction. It is resistant to cyanide in many cases. It is nearly resistant, or it has a very low affinity to CO, NO, H2S. These are the main signaling molecules in biological systems. So, for example, in our gut, we develop CO. You know, our body is able to develop CO to attack a bacterium. The E. coli will switch on the BD and will be happily living on. It's a defense factor. So, the first structure came out in 2016, not from the E. coli, but from a geothermos. And the first surprise was there because keep in mind what I said at the beginning, people have been trying to apply everything to the mitochondrial system. In the mitochondrial system, you have one heme, one copper, and the oxygen reaction between the two. So, well, no copper, let's put the two hemes. So you find a lot of literature where two hemes are one in front of the other, explaining that this is the oxygen side in BD. Now let's look at the structure. Can you see two hemes, one in front of the other? No. No? We know the active side is the D heme. Let me show this is here. We have two B hemes, but there is no second heme. So the whole catalytic mechanism that's understood until now, we have to overwork. It has a very high oxygen affinity. It catalyzes very classical reaction of oxygen to water coupled to the quinone reaction. And it has, as I mentioned already, a very interesting reactivity or non-sensitivity, if I may say so, towards molecules of the different physiological pathways. So this is our starting point. We have a system where we only have one heme that is reacting. So we don't know anymore what is the role of these B hemes. It may be electron transfer partners, but let's look into that. And of course, we don't know how electron and proton translocation is coupled. So let's start with the first type of measurements we do in the lab. This is equilibrium measurement, and this is indirect electrochemistry. So we use, you know that biological molecules are quite large, so we have or to find a way to put them close to the surface, or we have to add mediators for the indirect electrochemistry. This is a mediated electrochemistry. You take a window, a gold grid, a nanostructured gold grid, your sample, a second window. This electrochemical cell uses only 7 microliters of sample, which is very good for biological systems, of course. And since you can adapt the window, we can use it in the visible, in UV, in Raman, in infrared, and in fluorescence. Also, it's very, you can really take the same cell in different spectrometers. And you have no limitation by the size of the protein, which also in these big membrane proteins is a big advantage. It's actually a cell that was published first in 1990. We have been trying to make it change over the years, and we always came back to the same geometry. Also, maybe it's an ideal situation. So we can titrate nicely any kind of system. Here it's a BD oxidase. You have the contributions of the B hemes, very characteristic. And please note that the D heme has a shifted contribution, which makes it more easy to identify. So these redox titrations have been done. So let's start here with the BD1 from E. coli, which is kind of the system people like to take as a reference. And you have two potentials, very difficult to distinguish, and the D heme. So far, all is in line with what we know. Then we started to look into mutations together with our collaboration partners in Freiburg, from Thorsten Friedrich's group. And they have been mutating, and you see here the B595, which was before the partner of the D. In the old figures, it was the second heme that was the partner for the oxygen. If you make mutants, all of them, first of all, we check if all cofactors are in, because this protein likes kicking out cofactors, they're all there. We check if they're active, so the turnover with oxygen, all of them are active. And now, surprisingly, you have extremely shifted potentials. Or let's put it the other way around. The shift of the potentials is not surprising. The fact that they're active is surprising. So you can perturb the equilibrium potential by changing, this is for those that are not true biological, this is arginine mutated in asparagine, and you see that you have 200 millivolt shift. So it should change completely activity, it doesn't. So we are currently thinking that this heme is eventually not so essential for electron transfer. Next step, let's compare different oxidases. The BD oxidase is available as in all bacteria. So E. coli, very well known, we all have it. Geothermal denitrificans is living, it's an extremophile, and it is in a Japanese sea that you can find it, a lake, sorry. So let's look at the absorption spectra. Well, we have maybe some difference here. First hint, on the D heme. Something is not up. Then we made our titration like before. And now we see here a big difference. Look here. The B hemes are not so different, but the D heme, it's totally inverted. And when the student that was working on that, Anton Nikolaev, came with the data, I said, it cannot be. Some of you are a PhD student, you certainly have the situation before. You go to your advisor, you have a nice result, you have been working the whole night, and he said, no. Well, so Anton, he was very persistent. He tried again and again. At some point, I just sent it to our collaborators from the Max Planck in Frankfurt. I said to the colleague, listen, this is what we get. It was highly reproduced. I said, okay, he wasn't shocked. I said, why is he not shocked? Well, this is the structures. We have them in the meantime, so the colleagues in Frankfurt have them. I'm not sure if you can see it. So this is the E. coli, this is your thymus. Or maybe let me switch to the next figure because it's more clear. You have the same overall structure, and the D heme and the B heme are switched. So they're just inverted. Why are they inverted? There's a small difference in one helix only in addition. We think that the D heme is something that is created by post-translational modification, very difficult word, after the first oxygen reaction happens. And the oxygen pass, and let's go back to this figure, is not the same. Now, all this can be maybe rationalized, but what is really fascinating that both systems work. Right? You have a totally inverted heme potential, but both still have the heme D as a cofactor for the oxygen reaction. So this is on the list of things we don't understand. And this is just to say these are two BDs. There is in the meantime a structure of the tuberculosis BD. It's different again. So each BD is different. So, which is very interesting for ligand binding then. Okay, so this you have seen. Very interesting, by the way, for those that like working on hemes, we have lots of acidic residues close to the hemes here. It's very unusual. Yep. So here just an overview of what we know now. This is the most extreme case here, but still there are kind of a bit of difference between the different systems. Now, let's see what electrocatalysis can bring us. Let me quickly go. Well, this is trivial. I always show it, but I think for you this is really trivial. This is how creepy a cyclovoltamicro looks on a big membrane protein when you just attach it to a surface. But now, if you manage to get electrocatalysis, you get these nice curves, and you can get a lot of information of that, as you certainly all know. What do we do for demobilization? I told you those are membrane proteins. Still, we do quite classical things. So we typically will take gold surfaces and will adapt to the different charges on the surface. Typically, we try different types of tiles to see which one fits if we just want to physisope it. Or alternatively, we link it via the his tag. Oh, I'm sorry, the nickel, I don't know why the nickel got out of the side, but the nickel should be in here. So this is, his tag is something that is introduced genetically to the protein, and then you make kind of a counterpart directly on the surface, so you link it, you tag it to the surface. So this allows you to have a very stable linkage also to the surface. The nice thing on that is because we have a lab that does a lot of infrared spectroscopy, we can follow all these different steps by infrared spectroscopy, and at the end, and this is a very important question, we can see if it's stable or not, because the spectra are characteristic for the structure. There was a very systematic study done by Filipa Santos Seiza in the lab, who was trying to compare different nanoparticle deposition times and sizes to see what is optimal, because we wanted at the same time to have best electrochemistry and best spectroscopy. It turns out that the deposition time is the most critical one and changes a lot the intensity you get at the end. So let's not just show you quickly how we see if the protein is stable, because it's a very important criterion to be sure that we're looking at something coming from the enzyme. Then we have been also looking at how our structures look in more detail in collaboration with ICS in Strasbourg. We could see how the nanoparticles are organized on our electrodes. You see them here. You have certainly already seen this kind of picture. It's really a nice three-dimensional network where the protein then can work. And then, we, as I said, we change the surface with tiles or with the his tag. The protocol is very classical for this electrocatalysis, so it's a deposition of nanoparticles, immobilization, and attachment. We had the idea to make biosensoring with that, because these enzymes are very interesting. So we try to optimize the maximum. Still, it takes about 3 hours to have one of these surfaces. So one point that is very critical is the lipid. The lipid is kind of the solvent for the membrane protein. But in addition, it is also important for the catalytic activity. And some proteins, it really goes inside to ensure the stability. So Anton, who was doing this, he made a very systematic comparison of different amount of lipids. You always get a signal, but I'm not sure if it can be distinguished. Some are more stable than others, especially over time. So in our case, this was the optimum mixture, but it has really to optimize. So this is the only thing we found a bit more complicated when we're using membrane proteins. We really every time have to optimize this lipid ratio to study well. Once it's done, we can happily make electrocatalysis, and you see E. coli. Let's look at the blue one first. It looks like a quite classical curve. It's not perfectly homogeneous, but it's not too bad. And then we looked at our funny geothermos where the D heme is inverted. Let's look at that. Look at the black curve here. What can you see? A couple of crossovers. We have not yet a good explanation for that, but we believe that this is one of the reasons why this inverted D heme can work, because some first reaction is taking place, then you have a shift of the potentials, and then you have the next step coming in. So there's a coupled process in this geothermos system that was reproduced quite a lot of times. And when working on that, something funny was found. This is what you have just seen, a very complex cyclovoltammogram of the catalytic reaction of this BD. Then we played with temperature because it's an extremophile. Curve is not so beautiful. Then we changed pH, not beautiful. Then we did both, and you get a classical curve. So some protonation event seems to be guiding this BD oxidase from the extremophile. So just to compare, you see here, and this is glutamicum, which is very similar to E. coli in some sense. So you see it's very rich information in the electrocatalysis on these nanoparticles. Some a little bit, I'm not sure how many time, just a little bit to talk about inhibitor binding, because of course, as I mentioned at the beginning, what's interesting with BD is to look into antibiotics, so this is nothing else but inhibitor binding. There are three possible sites, the quinone binding site, and please let me add that quinone binding sites are very specific for each protein. So there is no binding motif. Several people try to find one. There is no binding motif. Every membrane protein has a different quinone binding site, and this is the most likely target. Of course, we also have the oxygen site, but this is a very unspecific site. And the proton channels can also be blocked. So we can, for example, work with NO, which is one of the signaling molecules. So you can bind it, and then it's released. And you can follow this also by electrocatalysis. So if you take a normal electrocatalytic curve with the oxygen reaction, and then you add NO, you will block the system, and a few minutes later, the NO is off. I just said, if we respire NO with our oxidases, a few minutes, it's not off. We are off, but not the NO. So you can use this very nicely then to determine, for example, the IC50 value of the NO binding and release. This was done by Irina Makachuk, who looked at a wild type and a large number of mutants to understand how the system is working. And one very interesting mutant that turned out is here in this area. This is the D heme, the oxygen, and most likely an O binding site. And she perturbed this system here, which is present. You see here many, many, many bacteria. You see how where tuberculosis, Megmatis, Subtilus, Typhion, they're not nice, huh? But they all have BD. They all have BD, and it's really funny. This is now just absorption spectra, and you see that the NO has a high pH dependency that is totally lost, for example, in this very simple mutation here. So the D58 is gone, replaced by a E. The whole system is perturbed. So something can be controlled by the proton channel. You see, I'm a little bit vague with some of my data because some of the data are very recent. The system is currently being completely overthought. I'm not sure if this word exists, but you may understand what I mean. We had a very clear understanding on BD 10 years ago, and now we have to really start all over again, and we are really finding some interesting things. Just as a last detail, before I run completely out of time, to see how rich this is, E. coli itself has two BDs, and it's not the only one. So it's so important that it has two of these kinds. They're not completely identical. The structures are there from both of them since 1.5 years. So we started, of course, let's give us some BD2. So Irina started to look. Let's agree it's nearly identical. So no big difference on AO mining. So this is not a reason for having two BDs. Actually, it turned out it is the pH dependency that is different. So at low pH, the one BD is more active, and at higher pH, the other BD is active. So it's a question of proton in the cell. So you see here the two, they are not identical, and now we have been very happy because it was again the site that we have just recently identified to be crucial for NO binding and for oxygen reaction. That is indeed the one that is different between the two. So one small site changed, just this one, the rest is the same, and you have two different enzymes expressed at different conditions for the resistance of the E. coli in the system. Let me just switch very quickly because, Veronique, you mentioned spectral electrochemistry on optical spectra, so I had to include this slide because we do a lot of infrared-coupled and Raman-coupled electrochemistry. Why? These are all amino acids in an infrared spectrum, very crowded, I agree. Here, this is where you see, the point is a bit weak, this is where you see the mid, but look at these two guys. They're really sticking their hands out. We are here. This is protonated acidic residues. Protonation, deprotonation, very nice signal here. This is what in theory you will expect. Let's look at BD. Do you recall at the beginning I showed you that close to the hemes are a lot of acidic residues? They're all here. All those that have a high pK, they are here. So we can use this, we have been doing these other systems to determine pK value of such a residue. Now look here, this is the wild time. This is our E. You see it really changes the environment. What does a shift mean, by the way? If you change the frequency of such a band of COH vibration, you change the environment and change the hydrogen bonding strength and eventually hydrophobicity. So it means the residues have really, when you make the mutation, you change the environment, which is enough to perturb the whole system. So last very quick point, we have been probing a lot of inhibitors to see if we can find something interesting. This is the most famous one, which is not specific. It blocks all quinone binding sites, so most quinone binding sites. And together with some collaborators, we tested some different ones. I have to honestly say that this is still the best, but several of them have been interesting passes. The orachines come from bacteria themselves. And they have been probed exactly with this technique we have been seeing, so the gold nanoparticles and the BD, and we have been sensing systematically the binding of the different inhibitors. So all this is published. If someone wants to know more about it, because I think I'm running out of time, I'm glad to send you the paper. But just to get a hint, in principle what you do is you mimic the quinone binding site or some intermediate state of the quinone binding site, and it should have a higher affinity than a quinone. Principle, it works. We have not found the inhibitor yet, so if someone has a nice idea of a quinoid system that could be tested, we will be glad to do so. Because, as you say, you know that development of antibiotics is a very long process, but still we should not give up because we need them at some point. We know that there are many resistances developing and that we need to find new molecules to block, and BD oxidase is certainly one of the big targets of the future. So here the inhibitor screening that was done by Irina, and then you go. So summary. So I focused here, as I said, I presented you the main techniques we have been using. So we have this transmission cell you have seen, which is an indirect electrochemistry. We have been working a lot on direct electrochemistry, on gold nanoparticles, and then we also combine this to different spectroscopies in the lab. It was applied successfully to BD oxidase and to other enzymes as well, of course. We have currently only one enzyme that is still resistant, which is the complex 1. But I'm sure at a later, maybe at another meeting, I can finally show you the electrochemistry of that one. But all the other enzymes from respiratory chain have been accessible with this kind of nanostructures. So this is why I'm very, very happy to have them, because before, electrochemistry on membrane proteins was very, very difficult. The surfaces were not suitable for that. So this is our perspective. Please let me thank you, my group. So Irina Marcus just finished her thesis. She's just here in front of the tree. Anna Filipa Santos did a very systematic study on the nanostructures to characterize those that are successful. It's a very important part. Natalia was also working here, and Ralph is now currently working on the oxidases. This is, you may recognize, it's Strasbourg. So if you like hot wine and this kind of thing, it's a good place to come. I have to say I'm very thankful to Frédéric Mélin, who is the main person in the lab working on electrochemistry together with my collaborators. And we have great collaborators here for the enzymes because we don't do the mutations ourselves. So this is coming from 2 German and 1 American groups. And of course, the financial support is also acknowledged. And I thank you for your attention.
Thank you, Petra, for this presentation.